Hello, welcome to chapter 4. In this chapter, we'll be talking about z-scores and what that means in regards to data as a whole. Last week, we talked about how we can use graphs and basic components of data to understand the whole picture. And now we're going to use the whole picture to help us understand individual participants or individual data points. So last time we used individual data points to see the big picture, and now we're using the big picture to zoom in. And hopefully that'll give you a really good starting point for what the heck a z-score is. So let's go ahead and get started. Last week we finished up talking about the normal curve. We're going to hit that again, hopefully understand some more nuances, and we're also going to take some time and slow down on it and not only understand it as a concept, but then try and build one of our own, build a normal curve of our own. The rule 68, 95, 99, that's going to come up several times, and we're going to talk about it again today. But then after we understand that normal curve really well, we can use that to understand individual scores, and that's when we get into z-scores and percentile ranks. And then we're going to finish up this lecture with some general important concepts to know. All right, so quick refresher. This is the normal curve. Whenever you get data and you do a good job cleaning it up, from outliers and making sure that your graph is scaled correctly, which means you choose the numbers on the bottom and the others, the x and y axes, you choose those numbers correctly so that your data actually looks as large as it should. You tend to end up with a normal curve. Not always, but very often you end up with a normal curve. Now, what does a normal curve mean? Well, it means that here, let me get my laser pointer out. Here you have the mean, which is the central mathematical number, the middle point, the average. And the mean is sensitive, but it's also the only form of seeing the average that is mathematical. So that's why we use it as often as we do. So this middle line, that's the average, which means most people score right here around the average. And then down here you see these numbers, -1, -2, -3, +1, +2, +3. Well, what does that mean? And what's that little symbol? Well, that little symbol means standard deviation. So this is one standard deviation or one standard average sized step away from the mean. And this is two standard steps or standard deviations away from the mean. And you can see that it goes in the positive direction and in the negative direction. This 0 is only talking about standard deviations. It's not meaning much else right here. So what are all these percentages then? Well, if you have a normal curve, and I am saying if, but for the purposes of intro stats, we're typically going to have a normal curve. You'll see that 34% and 34% of people are right around above and below the mean. The different data points, different scores, however, whatever we're measuring, 34% are within one standard deviation below and within one standard deviation above this middle number. And when you add them together, 68%, right? So when I talked earlier about the 68, 95, 99 rule, this is what I'm talking about. 68% of all of your data points are going to fit within one standard deviation, one above or one below the mean, the middle number, the mathematical average. So then what's this 13% on either sides of that? Well, if we go one more standard deviation out, so we've gone one standard deviation out, and now we've gone two, we have our middle 68%, but we can add this 13% and this 13% on the second, in this chunk, this second standard deviation away. We can add that into our total, and now we can see that roughly 95%. of answers will be within 2 standard deviations. So this blue, this lighter blue, and this darker blue, if you add them together, both above and below the mean, that's a lot of the scores. That's most of the scores. It's 95% of the scores. And again, if we add this third deviation away, we're at 99% of scores will be within all of that range. So let's talk more about what that means. What the heck this means when applied to individuals and applied to like a real story. All right, so now I have a different version of that same normal curve. It's a little bit emptier, but we're going to fill it in ourselves. We still have our middle arrow, which is the mean. And we still have our 1, 2, 3, and -1, -2, -3. Those are still our standard steps or standard deviations away. But now we're going to apply some real data to it and see if that clarifies what a standard deviation is. So over here on the left side, we have 100-meter race times in school track. I said applying real data. I totally made this data up. This is not coming from any school nearby. If you add all of these data points together and divide them out to get the mean, we will get this number, 13.86. Now, if you look at the data set, no one actually ran 13.86 seconds. No one did that. The mean is like an abstract number. It's a number that helps you measure other things. It's just the average. It's not an actual data point. It's not an actual person running the 100-meter. It's just a theoretical, a theory kind of driven number. So our mean, our mathematical average is 13.86. And if you continue through the process of writing out and doing the formula for the standard deviation, you'll actually get this number, 0.56. What does that mean? Well, that means if we take 13.86 and we add 0.56 once, just once, that's the first standard deviation away from the mean. That's one step away, right? So what is that number? 14.42, right? So we have our mean number, 13.86. Our first step away from that is 0.56 seconds away, which is 14.42. And then we're going to do it again. Another 0.56 away is 14.42 plus 0.56 equals 14.89. So that's 2 standard deviations away from the mean, and it's 1 standard deviation away from the first standard deviation. So the second standard deviation right here, 14.89, that's only 1 step away from 14.42, right? So 1 standard step. And then again, for that third standard deviation, 15.54. And if we look at our data set, no one ran that slowly. No one ran 15.54. The slowest number we actually have is only 15.1. which is a number that's right here in between the 2 and 3, right? It's slower than 14.89, but not as slow as 15.54. It's somewhere in the middle in this darker spot, this filled in spot. So that's how it works going positively, but it also works going in the negative direction. 13.86 again is our average, but minus 0.56 is 13.3. Minus 0.56 again gives us this number, 12.74. And for the last standard deviation in the negative direction, we have 12.18. Again, if you look at our data set, nobody ran that fast. So our fastest number is 12.8. That's actually not even 3 standard deviations away from the mean. It's right here close to the second standard deviation. The second standard deviation away from the mean. So now let's look at now that we have a big picture idea, we have our normal curve, we have our general numbers that tell us the large story of what's going on, what's average scores, the average times for our racers. Let's zoom in on 4 particular stories, and maybe now that we have this normal curve, we can learn more about these 4 stories statistically speaking. So let's go ahead and bring back that older graph that we were looking at before. That gives us a better idea of what percentages we're looking at. And let's look at our 4 racers: Johnny, Amir, Malik, and Zed. Johnny, Amir, Malik, and Zed. And each one has a little bit of a story. So let me tell you about Johnny. Johnny knows he's not the best racer, but he thinks he's pretty darn good. He thinks he's pretty darn good. And Amir hears this with his 13.9. And he hears this and goes, man, I must suck then. If Johnny's doing so well and I got a 13.9, I'm not keeping up with Johnny. I must suck. Malik has a 14.7, and he's pretty confident that he's okay. He doesn't want to be the best, but he's pretty sure that his scores are not going to bring down the team average at all. He thinks he's doing just fine, doesn't need to change anything about his workout regimen. And then lastly, our last racer is Zed with a 12.8. Now Zed is going so fast, he genuinely believes that a talent scout, a professional talent scout, is going to come knocking at his door any day now. Now, just for the purposes of our fake study here, talent scouts only show up if you are 3 standard deviations away from the mean. So 1 standard deviation basically means you're average. 2 standard deviations means, okay, you're kind of going beyond the average. You're doing a little bit more than that. And 3 standard deviations, those are the prodigies. So Johnny, Amir, Malik, and Zed. We have 4 race times here. Johnny thinks he's doing pretty well. Amir thinks he sucks. Malik thinks he's not doing great, but it's not like he has to change anything. And Zed thinks a professional talent scout is coming any day now. So let's go ahead and look at their scores, compare it to this graph, and see what we can learn about their averages. So Johnny has a 13.29 race time. Let's come down here and look at our mean, which is 13.86. He is faster than that. He is faster than that. So let's go left, less time. So we're going towards a negative down the scale because less time, means faster. So 13.3. He is faster than 13.3. So he's out of this first standard deviation. Johnny is out of the first standard deviation and into the second. But by how much? 13.3, that's the first standard deviation. He's out of that. He's past that, but he's right next to the line. He's right there next to it. So I think he can probably say, yeah, he's a good racer, but let's be careful before the confidence gets too big, right? Now let's look at Amir's score. Amir has a 13.9. And let's look at our mean, 13.86. Well, he's slower than that, so let's go down the line this way, 14.42. Well, he's faster than 14.42. So Amir is within this first standard deviation. He's within this first standard deviation. And remember, if you are within that first standard deviation, if you're in this dark blue zone, you're considered average. You're considered average. Some people hear the word, hey, hear the sentence, you're average, and they think that's an insult. But remember, we're being statisticians. We're being statisticians, which means I'm trying to tell you the truth. Amir, you have nothing to be ashamed of. You are average. You're running as fast as 68% of the population, and faster than these 2 standard deviations. So you're doing good. You're doing good, Amir. Next, let's look at Malik and his score. Malik's score, 14.7, while the average is 13.86. And he's slower than that, so let's go to the next one, 14.42. Malik is slower than that, 14.89. Okay, Malik is faster than that, so he's somewhere in between these two. He is in his second standard deviation away. He is more than one standard deviation away. He is in the second standard deviation. That means he is indeed changing the average of the team's scores. He should probably jump on doing a little bit better, figuring out a new way of approaching his workout before he gets even worse and keeps bringing the team average down. So maybe Malik's idea of what is going on needs to change a little bit. Finally, let's look at Z. Let's look at Z, 12.8. 12.8. Remember, talent scouts only show up if you're in the third standard deviation away. Third standard deviation. So you have to be not just one step, not just two steps. You have to be beyond 2 steps away from the mean. He's got 12.8. So let's start at our mean. We're going to go faster than that by 1 standard deviation. That's 13.3. He is faster than that. And the next one is 12.7. Zed got 12.8, so he's not faster than this. He's also in this second standard deviation. He is faster than the average. He and Johnny both are faster than the average. Johnny is barely faster than the average. Malik is close to breaking that boundary and into the next standard deviation, but at the moment, he is not. He is fast, but he's not quite professional scout fast yet. What's another way of understanding these scores? What's another way of understanding these race scores? Well, we can look at their z-scores. A z-score is looking at someone's standard deviation score, if that helps. So Johnny is faster than by 1 standard deviation. We looked at that. So he is at least 1 standard deviation away. But how much of a standard deviation? He's 1.02. So he's barely past that first standard deviation, just barely, right? On the mirror score, we have a 0.07. That means he is 0 standard deviations away from the mean, which means he's average. It means he's average. Malik, his z-score is 1.5 away from the mean. That means he's 1 standard deviation and another half of a standard deviation away. He's 1 and another half standard deviations away from the mean. That's a lot. That's a lot. So he is changing the scores for sure. And Z, he's our final z-score. He's got a negative 1.89. 0.89. That means he is real close to 2 standard deviations away, but then there's a whole new standard deviation before he's at that third level, right? Because professional scouts only come for the third standard deviation away. So a z-score is giving a standard deviation score to a specific data point. To a specific data point. So Johnny has a specific data point. Johnny gets a specific standard deviation score. Johnny has a z-score called at negative 1.02. He is 1 standard deviation away plus 0.02, so he's just barely past that. And this is what a z-score is. This is what a z-score is. A z-score tells you exactly how many steps they are away from the mean and in what direction. A percentile, because you'll see that a few times, a percentile is different than the z-score because the z-score is about standard deviations, right? Standard deviations. Percentiles is about other people's scores. So let's look into percentiles real quick. So a z-score was giving someone a standard deviation score away from the mean, right? A percentile is not about the mean. It's about how many raw data points are above or below a given person or a given score. So what does that mean? Well, if we keep with our fake illustration, our fake racers, Our original race times plus the new racers equals 16 data points. We have 16 participants in our study. We have 16 numbers to compare to one another, right? So I already went through the process of adding in Malik and Johnny and Amir and Zed to the original list of racers' scores. And now all we have to do to get a percentile rank is we look at that person's score and we count how many people scored beneath that. Do some basic division and then you have a percentile, right? So let's start with Malik, right? Malik was a very fast racer. Malik actually tied or was very close to this other racer. That means there are 14 racers slower than Malik. Well, Malik has 14 racers slower, divided by the total number of data points. That's divided by 16. So 14 divided by 16 equals 0.875, and you turn that into a percentage. Malik scored in the 87.5%. Right, that's his percentile. Amir has 8 racers below him, so if you can count 1, 2, 3, 4, 5, 6, 7, 8 racers below Amir. 8 is divided by 16, the total number, and that gives you he's in the 50th percentile. Like, that is very close to dead average, dead center. And Zed only has 1 racer slower than him, so he's in the 6th percentile. 1 divided by 16 equals 6%, 6.3%. So there's a big difference between z-scores and percentile ranks. Z-scores is that score you're given based on the standard deviation, which is an average on that normal bell curve. The percentile ranks, those are based on how many people you beat. There's no mathematical averages about it. It's just how many people did you beat compared to the total number of people who tried this out. So if you think about SAT scores, a lot of people say, well, I scored in this percentile and this percentile. What does that really mean? Think of that as like I scored better than 87% of the people who took this SAT across the nation. Or if you're seeing that you scored in the 50th percentile, that means you're in the dead center of the race, right? You have 50% of the people who took the SAT scored below you. Now, the fun thing about percentile ranks is you can invert them and still get more information, right? So for Malik, he is 87.5 percentile rank, right? So if we take 100% minus 87.5, if I do my math right, I believe that is 12.5%. That means 12.5% are faster than Malik. Malik beat 87.5% of racers, and that means 12.5% of racers are faster than Malik at the top end. And you can do that reversing of percentages for any percentile rank, right? So for Zed got 6% below his score. That means there's more than 93% who scored above him. More than 93% of racers were above and faster than Zed. So how many individual scores are given below a specific person? And this is more about the sample size. It's not about mathematical averages. So let's go ahead and wrap up this lecture with some important terms to know from Chapter 4, operational definitions, questionable research designs and decisions, false, true, positive, negative. That looks like a lot of words that don't mean anything, but I'll tell you more about that in a moment. Operational definitions. So what the heck is that? What does it mean, and how does it apply to statistics? Well, I like to start with a silly definition first, and then kind of get more serious after that. So operational definitions, what are they? Well, in a silly way, you take really complicated stuff and you turn it into numbers. That's all it is. And I know that doesn't sound helpful, but in a way, it really is the only thing an operational definition is. More seriously, it's a precise way to measure complicated concepts. Complicated concepts. So let's look at some examples that I have here. If I ask you, hey, do you have a valuable car? Do you have a valuable car? The first thing you should say is, what do you mean by valuable? Right? Valuable can mean lots of different things to lots of different people. So we have to operationally define the word valuable. Does that make sense? That should help a little bit. We're not just using this big, vague concept called value. We are coming up with precise ways to measure value. Well, what are some precise ways to measure value? Gas mileage, right? That you can. Those are precise numbers. You can count up the number of utility options, like how many extra features are in that car. You can count those, and because we're counting, that's precise. That's what makes it a precise way to measure the concept. Some people like to look at horsepower, braking speed. Some people like to measure their car based on how low it is to the ground or how high off the ground it is. And you can measure those things in inches, right? And now that we have a precise way to measure those, that would be some pretty solid operational definitions. Um, and it really is that simple sometimes, and it is also much harder to operationally define things in other situations. So if I ask you, do you have a valuable car? Well, we can operationally define that in a lot of different ways. But if I ask you, are you happy? Wow. How do we apply numbers to happiness? And how do we precisely measure someone's happiness compared to someone else's happiness? How do I know that I'm happier than you, and by how much? Or maybe you're happier than me. But how do you know that? And by how much? Did you measure your happiness with a ruler? Did you measure it by and this is where it gets harder to operationally define things. So psychology uses a lot of tools, and sometimes we use multiple definitions and multiple measurements depending on how complicated something is. So happiness being very complicated, we might use multiple tools to help measure that. One way to make it precise is maybe measure how many times somebody laughs in an hour, right? You can click 1, 2, 3, 4, 5, and you're at those, so those numbers stay precise, and you're keeping it within an hour, so that's consistent measurement. But that's not the only way to understand happiness. Some people are just louder than others, right? So maybe we could look at how many times someone smiles within that same hour. Or maybe we can ask them to their face, hey, you tell me, do you feel happy? On a scale of 1 to 7, right? We call those Likert scales. And some people really enjoy or appreciate Likert scales. Some people really hate Likert scales. I'm going to leave it up to you in your professional judgments and your next class on research methodologies to come up with your own ideas on what you think of Likert scales. If I ask someone, hey, how happy are you on a scale of 1 to 7, is that truly a precise measurement of their happiness or not? And that's just something every researcher, every statistician has to wrestle with, right? You have to ask these questions. Did I operationally define my concept well, or did I make a mistake? Or did I make a mistake? A good researcher should be open to critique and input from others on how they've defined their terms, and they should be very clear about how they define their terms in their research articles or papers. The best way to grow is to just put put it all out there, put your full confidence out there, and let people kind of tear it up and just grow from that experience. So that's operational definitions. It's where you take a big concept and define it with terms that you can now operate with precise measurements that you can operate with, therefore operational definition. All right, so next we're going to talk about false and true, positives and negatives. False and true, positives and negatives. So whenever you're doing statistical research, you're pulling a sample from a population and then running stats on that small sample. Sometimes you can run stats on the whole population, but most of the time you're kind of stuck only grabbing a few people or a few data points and running your stats on that and letting your sample represent the whole population. What's the reason for that? Well, it's just not feasible to run stats on a whole population all of the time. If I wanted to know the average shoe size of every Amazon employee that ever has been and ever will be across every warehouse across the whole world, I just don't have that time to go to every employee and ask their shoe size. And even if I had a team of researchers, I don't have the time to go ask every shoe size there was. What I could do is I ask a few Amazon employees from different warehouses, and then I let those few represent the averages of the whole. But in the end, it's still just a sample. In the end, I could get really unlucky and only ask the Amazon employees that have the tiniest feet. Even if I ask 100, I could get really unlucky and only ask the 100 smallest feet employees of Amazon, and therefore not actually get an idea of what's really happening with the size of feet in Amazon employees, which is a really weird topic to care so much about. But I'm hoping the illustration works in telling you that samples sometimes don't reflect the whole population. The sample does not always reflect the whole population, which means sometimes you can find a statistical significant finding. Like you can do the stats, run the analysis on your experiments, and find something that's really significant. Have a positive finding, but it doesn't actually reflect the whole population because of a sampling, an unlucky sampling issue. So in that case, we would say you have a false positive finding because it's a positive finding. Yes, there's a difference in what you found, but it's false because it doesn't actually represent reality. And so over here, we have this Punnett square I made up for you guys, positive and negative findings. And then we have true and false, which is this true and false is talking about reality, what's out there in the whole population. Positive and negative is talking about what you found statistically. And so we have here in this bottom left corner a false positive. In this positive column, we have a false positive. That means you found something that isn't actually there. It's every statistician's worst nightmare. And it should keep you up at night because then you find yourself doing better research in the future and maybe doing something really important called repeating your analysis and getting a new sample and checking to see if your numbers were correct. All science should be replicable, right? So if you ever find yourself with a positive finding, you should always ask, was it a false positive? Could I get a different sample and get the same finding? Now, if you do get a true positive, that means, hey, you actually did it. You've statistically found a difference, and that statistical difference is actually happening in reality. That is every researcher's dream come true, right? You did it. You found a real difference in your research, and it reflects reality. True positive versus that false positive, which is kind of a nightmare zone. But there's something else over here, like a true negative. a true negative. Sometimes you run research and all of your statistical findings come up with, no, there's no difference here. So that's a negative finding. But it could be true in the sense that, no, there is no difference, and that's true in reality, that in reality there is no difference between what the variables you were looking at. And to those, I say this: you still did it. It's not as exciting, but it's still good science. It is still good science to find a negative finding as long as you're representing your population well, right? And then we have this last category over here, a negative, a false negative, a false negative. What does that mean? A false negative means you, in your stats, you didn't find any difference, or you didn't find anything happening. But that's not what's happening in reality. There is something happening in reality, you just missed it statistically. So a false negative might be something like looking into, well, I think that average height correlates with average number of fillings in people's teeth. And then you go and you do your research and you find out that there's no correlation between height and number of fillings people have in their teeth. But a false negative means there actually is a correlation. You just missed it in your sample. So, false and true, positive and negative findings. Positive findings means when you ran your research on correlations and whatever else is going on, you found a positive finding. Negative means you didn't find anything really all that special. True means you're doing a good job reflecting reality. False means you're doing a bad job reflecting reality. False and true, positive and negatives. All right, our last slide for today, we're going to talk about questionable research, which I know you see that and you should have this response. Wait, professor, instructor, we're supposed to be as ethical as possible. We shouldn't be conducting any questionable research. We should only be having the highest level of ethics. To you, student, I say you are brilliant. And yet we should still talk about questionable research. Why? Because sometimes it's kind of unavoidable. Sometimes people use questionable research practices on purpose to get what they want, to get what they need, to get the grant that they want, to advertise what they want, to sell what they want. And to know the difference between someone who accidentally had to make this bad choice or someone who is trying to manipulate you is why we talk about questionable research at all. So this is definitely a topic you're going to hit a lot harder in other classes like ethics class or a research methodology class, but it's still worthy of talking about here in statistics because in statistics there is a way to represent reality in mathematics that is more or less ethical. So it's a lot of people see stats as just like a whole bunch of formulas, and it is a whole bunch of formulas, but how we go about conducting our statistical analysis also requires some level of ethics from us too. So we're going to talk about questionable research practices. There's four main categories I want to hit today: sampling, statistical, exaggerating results, and definitions, operational definitions to be specific. And we're going to jump right into sampling first. So when it comes to sampling, the two I want to talk about today, it's not the only way to mess up sampling, but the two biggest ways to mess up sampling would be to mess up sampling who you sample and to mess up why you're sampling those people. So comparing like, let's start with comparing like. So comparing like means comparing apples to apples and oranges to oranges, right? You don't want to compare groups that are so different that they don't have any common ground with your statistical questions. You want to make sure that you're kind of finding the bridge point with your stats. For example, if I want to measure athleticism, well, I can define that by saying how much weight someone lifts. Well, I don't want to compare cross-country athletes to football players. I don't want to do that. Why not? Well, the sports are so different. They ask such different things from their athletes that I won't actually learn much. I mean, obviously, the professional football players who spend most of their professional careers lifting heavy weights will score higher on my heavy weightlifting athleticism scale. Whereas cross-country runners who only typically lift to maintain balance or get just enough strength to help with their techniques or strategies don't lift nearly as often and therefore won't score nearly as high as the football players. And what am I going to learn from that? Nothing, because that's just how those people have been training their bodies over time. So that's comparing. That's a mismatch in comparing groups. But there's another way to mess up sampling. There's another way to mess up sampling. This one I call pulling obvious. Pulling obvious. So a pulling means you're grabbing participants for a sample from the population. I'm pulling from the population to make a sample. Now, you want to do this randomly. You want to do this randomly because you want to represent the whole population. You don't want to sample people that you kind of were easy for you to grab, or obviously you're going to answer the way you want to answer. Some people have done this when it comes to like really hot topics in politics. Like the conservative right has been known to sometimes find the most insane like leftist ideas that don't actually represent most of the left political agenda. They just find the ones that are so outlandish or have criminal records that they're really just pulling the ones that tell the narrative anyway. And the left does this too. The left does this too, where they'll go find the conservatives that say the craziest things and only ask them questions. I call this pulling obvious. You're trying to tell a story and you're sampling not randomly, you're sampling specifically from the place that's going to get you obviously the answer that you want. So those are the two big problems with sampling. Got to make sure that you're comparing groups that are appropriate to compare and make sure you're randomly sampling. The next one down is statistical questions, right? Statistical choices. In last week's chapter, we saw that we were looking at fake data about incomes across Kentucky County. And there were a couple incomes that were so off the charts, it actually messed with our statistical data and no longer represented the reality of what was happening in Kentucky's county. It was fake data. But the point is, this actually happens in reality too. There are some people in a state or in the country who make so much money that it changes the average for the rest of the nation or the rest of the state so badly that it no longer reflects the reality of what's going on. So what do you do when you have one person whose score is so off the charts that it no longer reflects the reality of the rest of the population? Well, one answer is you delete the outlier. You omit that score. Why would you do that? Well, we're trying to understand the population really well. And if one score is making that muddy, then I don't want to look at that one score. I want to look at the population. I want to get those averages correct. So it seems kind of weird, but you definitely want to delete sometimes. But then the question is, well, how much do I delete, and when do I stop deleting, and what do I do with those deletions? Do I just like get rid of them and ignore that they ever showed up to my survey? We'll talk about that in a second too. Another big one for the statistical side is look at effect sizes. Look at effect sizes. Someone can say, hey, racers who drink this Sunny D are faster on average than racers who don't. They might be statistically accurate in saying that, but the effect size is, okay, but how much faster are they? How much faster are they? Could it be like by a millionth of a second? And at that point, isn't that just luck and not really a statistical difference? So that's why you gotta look at effect size and deletions. And there's also some upper level analysis choices that statistically we have to be aware of. Not for this class, but in the future classes to know how to best represent your data. The next big category is exaggerating results. Exaggerating results. So, this is true or untrue, therefore I'm going to jump over to this next logical jump. In statistics, I want you guys to be very humble. When you have a finding, it really only means this finding, and that's it. It doesn't mean anything else. It's really easy for scientists, it's easy for myself to fall into this trap that when we see data that we like, we then make a logical step and say, this must also be true, or this must now be untrue. But really, when someone has a statistical finding, they're only talking about their statistical finding, and that's all it means. So a quick example of this that I actually saw from where I am here in Central Kentucky, I have seen it said many times, there are no undocumented immigrants in this county. Therefore, we don't need social support programs for undocumented immigrants because we don't have any. And the first thing we should say is, well, how hard did you look? How hard did you look? How did you sample? Did you sample conveniently? Did you pull obvious? And even if you didn't, and you did all the work really, really well, and you sampled randomly, and you found no evidence of undocumented immigrants here, how would you know that they wouldn't show up to get support once you started the support program, right? So after you have support programs in place, people might show up to receive those supports. They might have those needs, which is why when someone has like a statistical finding, they should stop at that statistical finding. If someone says, hey, we have no undocumented immigrants in this county, we have to be careful with the next therefore. We have to be careful with the next logical step because that next logical step is no longer statistics. It's no longer statistics, it's something else. Sometimes you gotta make choices based on stats, but you gotta be real careful when you do. You gotta be real careful when you do. And lastly, we have bad definitions or definitions that are shaky or bad operational definitions. Well, what does this mean? I actually have a really good example. I once read an article by an institution I shall not name, but they are a big, big institution, and they claimed that people who support Trump and vote conservatively are more likely to be psychopathic. Psychopathic. First of all, as a psychologist, I'm like, are we using this medical term as an insult? Because that's wrong. It's just a medical term. And the second thing I had to ask was, how are they defining psychopathic? And wouldn't you know it, they define psychopathic based on interpretations of value systems, on belief systems. So if someone disagreed with their worldview, with the surveyor's worldview, they automatically got defined as psychopathic, which is a bad definition of psychopathic, and it's a bad way to define people who disagree with your viewpoint. Bad way to disagree with your viewpoint. I'm not here to say I'm pro-Trump or anti-Trump. I don't care about any of that right now. But I am here to say that's bad science. It's bad science when you define things poorly just to make a point or just to make your own narrative or story come out. So, in the end, sometimes you gotta just do it The best thing you can do in these situations is report it. Sometimes you can't sample randomly, so you gotta report it in your paper. I did not sample randomly. Sometimes you have to delete scores from your stats. You should report that in your paper, right? Initially, I had 500 data points, but 5 of them were way past my um, acceptable level for an outlier, and I deleted these 5. Here's what those 5 scores were, right? You report it in your paper. Don't exaggerate results. You can just ignore that entirely. But even when it comes to operational definitions, sometimes you kind of have to settle with a bad definition and get started on the work, which sounds weird. But let's go back to that happiness definition. How do you define happiness? Man, professional psychologists have been working on that for decades now. We're further along than we were in the past. We're further along than where we were in the past, but that doesn't mean we're there yet. So sometimes the best thing you can do is, here's the definition I'm working with, and you you report it, you put it in your paper. Here's the definition I'm working with. I think it has a weakness here and here, or I think it has a strength here and here. You just put that in your research paper, and you move on, and you do your best. Someone's gonna get mad at you for it. You listen to them, you adapt, and you repeat the you repeat the science over again, and you repeat the project over again, and you just keep trying, doing better every time. That's all I've got for you guys today. I hope to see you again soon. Remember, message me on Blackboard if you have any questions about any of this. Take care.